Well, welcome back. Now let's look at the classification process in details. Right. So we divided the classification into three steps. The first one is pre-processing and feature engineering. So basically, you generate the feature vectors. And the second step would be train the classifier. And the third one is evaluate a classifier. Now let's look at this with an example. So this example is the same as in Lab 3, where Lab 3 will be released in either Tuesday or Wednesday. But so basically, for the raw data, we have the category, which is the label, and the description, which is just the document. All right. So as the category, we have, for example, MISC and rest. Rest means restaurant. So the sentence is about a restaurant. MISC is miscellaneous or more or less like other. So other topics. All right. So the task is to predict the topics of the sentence or the document. So these are the sentences. Okay, these are the sentences. So as the first step, we firstly, because in this example, we firstly kind of tokenization. So we tokenize the original sentence into a set or a list of words. All right. And as you can see here, all right. And after that, we count. We do the word counting. We count the frequency of each word. And we also apply other features. That's why we've got these features. So it's essentially the X here, the feature vectors. And the labels, as you can see, we assign 1 to MISC, and we assign 0 to REST. So you've got the labels and you've got the feature vectors. All these are from the raw data. Okay, so this is the first step. You generate the features and the labels. So by feature engineering, it actually means that when you generate the data, feature vector, you need to select like which feature would be more useful. For example, in this task, as you can imagine, because we're going to predict the type or the topic of the sentence, some words, for example, the here or the is here, they most likely they show up in every sentence, and they're not that informative regarding to this specific task, right? So as part of the feature engineering, we can actually remove these words, or we remove the stop words if you know what it means. So basically, we just remove this commonly seen words. That's it. That is a feature engineering example for this task. And for other tasks, for example, when you do medical diagnosis, so the human being, the person's, you want to generate the feature vector for a specific person, then let's see. Okay, so her height, weight, age, that would be useful or important features. But let's say the color of her eyes or the color of her hair should not be or usually is not very important, right? So it should not be included in the feature engineering in the feature vectors. The reason that we want to only keep those important features is that we can reduce the size of the data, right? And even, I mean, we use Spark in a big data manner. It is still meaningful. I mean, we don't need that much. If we can avoid to handle that much data, it would be better. Right. So this is the first step, pre-processing and feature engineering. The second step would be train a classifier. So when train the classifier, the input is the training data, which includes the feature vectors and the labels. We use a classification algorithm to get the classifier, which is fx. Right. And we can use the classifier to do the prediction, even for the training data. As you can see, the prediction may or may not be the same as the true labels. That is possible. Right. Because as the classifier, we're not trying to because when we train a classifier, we're not trying to make sure that the prediction of the classifier would be the same as the labels in the training data. First of all, it may not be achievable. Secondly, even you can achieve that, this may or this indeed most likely it will lead to overfitting. All right. So when we have the prediction here and the labels here, we can compute the precision, recall, and F1. Right. For precision, we predicted 3 ones, where 2 of them are the same as the label. So the precision would be 2/3. And recall, there are 3 ones in the training data or in the true label, and we have successfully predicted 2 of them. So it is 2/3 as well. And F1 is the harmonic mean of precision and recall. So as they are the same, the F1 is 2/3, 0.666 as well. So this is the second step when you train the classifier. And when the classifier has been trained, we evaluate the classifier using test data. So for test data, we kind of do the same thing, right? We use the same procedure. So these are the raw data. We generate feature vectors and labels, right? And as you can see, the data here would be different from the data in the training example. So in the training data, right? And we're using this test data as input of the classifier, right? And we got the prediction, right? So the feature vectors as input to the classifier, we got the prediction. The prediction is 4 ones and 1 0. So the precision would be because for these 4 ones, 3 of them are true. So the precision would be 75%. Recall, we have 3 ones in the true labels, and all of them have been predicted correctly. So the recall is 100%, and the F1 you can compute it as 0.86. Right. So this is how you evaluate your classifier. And I need to point it out that when you really use the classifier in a real application, the input data would have no category, right? Only have the sentences. In that case, all you need to do, because your classifier would take X into the classifier. The classifier is essentially fx, and so it will output Y. Right. So you just convert the sentences into feature vectors, and you put the feature vectors into the classifier. You get the prediction. Right. Just that simple. All right. So these are the 3 main steps of classification. And you will see it in lab 3, and when you do lab project 2, it is also closely related. You need to know these steps, especially, I mean, because the project and the lab are also trying to solve this text classification problem. So you need to know how the original data or the raw data, raw text looks like, and how you convert it into features. Well, for this part, we will introduce a little bit more in later in today's lecture. All right. So the next topic would be how do we judge a model? So here, the first thing that we need to know is what is a model. So basically, the model and the classifier are different concepts or terms. Right. So in short, I mean, one model could have multiple classifiers where each of them has different parameters. For example, if let's say fx equals to w transpose x plus b. So for w1 b1, that could be a classifier c1, and for w2 b2 it could corresponds to classifier c2, but they all belongs to one model, and this model is fx equals to w transpose x plus b. Right. So what is the different model? Because as you know, as you may know, there are different kinds of classification methods or classifiers. Or in neural network, you can have different network structures. So all these things, they are different models. Right? They are different models. But as long as the model is fixed, means, for example, the method is fixed, or say the neural network structure architecture is fixed, then the different parameters will lead to different classifiers in that model. So classifiers can be trained through the process 2 here, but the model is chosen before that. And once you choose the model, you can't change it. I mean, you can't change the model. All you can do is you fit in the training data, and it will generate the classifier. So how do we choose? How do we know which model is good? How do we judge a model? So that would be a problem, because different models have different characteristics. Some models are doing well on some tasks, but not on other tasks. So when judge a model, the first question would be, should we based on training error or testing error? Right. So the answer would be straightforward, because if we rely on training error, then it will lead to overfitting, because the goal is always minimize the error. So when you minimize the training error, you're trying to fit fx to the training samples as good as possible. In that way, I mean, it most likely it will lead to an overfitting, because you are kind of ignore the generalization. Right? So when judge a model, we should based on the testing error, and this is when we judge a model. But if there are multiple models to choose, we need to know which one is better. But at that point, we may not have testing data. All right. So in this case, we further split training data or the whole data set. Let's say we split the data set into training data and development data. So basically, we've got a development data or development set from the training set. Okay. And can we trust the error values on the development set? Because when we split the development set from the training set, we will train our classifier on the new training set and evaluate it on the development set, and using the result on the development set to choose a good model. So ideally, I mean, if we want to have more reliable results on the development set, then we want the development set to be large enough. Right? But when we have a larger development set, because the development set is split from the training set, means we would have less data for training. And as you may have known or not, the number of data, the size of data for training directly affect the performance of the classifier. So in general, the classifier would need as more as possible training data. All right. But if we preserve a large development set, then the training set would be smaller, and hence the performance of or the quality of the classifier would reduce. So in order to handle this case, in order to use as more as data to evaluate or to help choose the models, but without losing too many training data, so the k-fold cross-validation is used. The idea of k-fold cross-validation is simple. So these are the total data or the data set. We kind of divided the data set into k-folds, into k partitions, k partitions that are not intersect with each other. Right. Let's say if k equals to 5, we divided the training data into D1, D2 to D5. Right. And at each iteration, so there would be k iteration, we use say in iteration I, we use DI as a development set or test data, and we use D minus DI, so all the rest parts or rest partitions, as the training data. So as you can see here, for iteration 1, the first partition is used as test data, the rest is used as training data. Iteration 2, the second partition has been taken. Iteration 3, the third one, and for iteration k, the last one. So in each iteration, only one partition will be used as the development set. So in this case, we can always guarantee that there are the number of training data would be k minus 1 over k times the total size of the data set. So that is not too small, right? And after k iterations, we kind of use all the data as development data for once. So we kind of evaluate the model on all the data, on the development data, which is essentially all the data. Right. So the total or the measurements that we're going to use to evaluate the model would be you can use sigma, or you use average on on the performance on the test data of all k iterations, or on the performance of the development data on the k, or on all the k iterations. And we can use this as the measurement to measure the performance of the data of the model, and to help us to choose the model. Now let's look at a concrete example, which is text classification. Let's start from the problem itself, and in today's lecture we will introduce how to use naive Bayes. That is a commonly a well-known classification method to solve the problem. In order to give you an overall, or give you a sense of how this machine learning thing works, right? And also this in project 2, we will do exactly this, or at quite similar tasks, which is also a text classification tasks. So hopefully it will also help in your project 2. So the application of text classification is very wide. For example, assigning subject categories or topics, or genres, a spam detection, authorship identifications, or to identify the author of this article or document, age, gender identification, language identification, sentiment analysis, so the attitude is positive or negative. And I think you can work out the corresponding labels to different applications, all right? And the input data would be usually the same for text classification. So basically it's just a document or a sentence. So you can view sentence as a short document. I mean, in this case, they are all the same, and you have different labels for different tasks, right? And as I said, we will do this in project 2 as well. So the problem definition, or more official problem definition of text classification, is that so the input would be a document or sentence. We use D to represent it. The output would be a class label C that is in the set of C1, C2 to it depends on how many depends on the task. So how many different labels you have. All right. So the classification methods could be different ones. Today we will look at naive Bayes. And there are logistic regression and SVM and even decision tree, etc. So these two will also be used in project 2. Right. Now let's look at naive Bayes. Right. So the intuition of naive Bayes, so that it is a simple classification method. So that's why it's called naive. Based on Bayes rule, so that's why it's called naive Bayes. Right. It relies on a very simple representation of document, which is a bag of words. So basically, this is the document, and you can imagine it's like you threw the words. You do the tokenization. You threw each and every word in a bag, right? And so essentially, you just count the occurrence of each word or the frequency of each word. Now, so what we want to predict is that given document D, we want to predict the class label C. So it's the probability of C given D, right? And you can you can imagine if we can know that the probability of C1 given D, C2 given D, and C given D, then we pick the maximum one, which is the most likely one. It would be the prediction result of this classifier. Right? So it's all about to compute the probability of C given D. So according to Bayes' rule, this probability equals to a probability of D given C times the probability of C divided by the probability of D. Right? So we want to know that which class is most likely, as I explained here. So basically, we want to know that the argmax of C, the probability of C given D. Right. So this MAP stands for the maximum posteriori. Right. It is just the most likely class. So this is what we want. And according to the Bayes rule, so this one equals to this, and we can drop the denominator because it is always the probability of D, where D is always the same, right? Because for C we can have different C, but as I have explained here, these are all the D are all the same, so D can be dropped. Here we comes from this, and as if you have remembered, so for D we represent it using a bag of words. So we represent it as the frequency of each word. So it is so D is represented as x1 to xn. Then we kind of convert the formula here to here. Now this one have how many parameters? So we need to compute the probability of x1 to xn given C. So this C is number of classes or number of class labels, and all the different combinatorial of x1 to xn would be C for each xi. The size is, because it is a vector, so the size is x, and we have n of them, so to the power of n times C. So the parameters here would be extremely large, right? And in order to because we have this much parameters, so we need a very large number of training examples to estimate the parameters here. All right. So that's why we need to continue simplify the formula here. But in order to do that, we need some assumptions. Right. So basically, we need two assumptions here. One is that the bag of words assumption, where we assume that the position does not matter. And the second assumption would be the conditional independence assumption. That is to assume that the feature probabilities, that is probability of xi given cj, so this is for a particular term, the frequency of the term given a particular class label, are independent given the class C or Cj. Actually, it should be Cj here. Means given the class Cj, the feature probabilities for different xi are independent then we can rewrite the probability like this. So this is just a simple statistic, and all right. So now we have converted this formula to this one, right? And because so given a test document, let's say positions are all the word positions in the test document. So then we can compute the probability, the predicted class label using naive Bayes classifier. So it would be argmax CJ in C, probability of CJ times the probability of xi given CJ for all I in positions. So the mathematical derivation until here is simple and straightforward. The next thing is to compute or estimate these two probabilities. Right. So in order to learn the multinomial naive Bayes model, essentially we're going to estimate these two probabilities. And let's use the first attempt would be using MLE to estimate the probability. The probability here. So before that, I need I would see a little bit more about multinomial naive Bayes model. So basically, if we are using bag of words, then the naive Bayes model is called a multinomial naive Bayes model. If we are using, say, for example, the bag of words would be a number. Sorry, the frequency of each word in the vocabulary. But if we only use whether the word has occurred or not occurred in the document as to construct the feature vector, then it would be called a Bernoulli naive Bayes model. But anyway, I mean that is to distinguish two different naive Bayes models. But in this lecture and also in the project, we will consider a multinomial naive Bayes model. All right. So basically, in order to estimate the probabilities here, we simply use the frequencies in the data. So for the probability of CJ, because it is a prior probability, it would be considered as the number of documents that have CJ as its label divided by the total number of documents. So it's a fraction of how many. So it's a fraction of how many documents that have the class label CJ. But then for probability of WI given CJ, it should be the fraction of times that a word WI appears among all words in the documents of topic CJ. So it's count WI within CJ divided by the sum of count W in CJ, where W is in the vocabulary. So it means that for all the documents that are labeled as CJ, how many of the fraction of word that is WJ. Right. So in order to speed up the computation here, because here we have a summation, we can create a mega document for topic J, for each topic J, by concatenating all documents in this topic, right? And then we can use the frequency of W in these mega documents as to replace the summation here. So basically, it would be the frequency of W in this mega documents J. You would create the number of the number of mega documents would be equal to the size of the label class label. Right. So the problem of above method is that if we have seen for example, given a word fantastic, if there is no training document that contains the word fantastic and classified in the topic of positive, then the probability here would be as we use the formula from the previous slides. The problem is that the count of fantastic given the topic is positive, this one is 0, which will make the probability of fantastic given positive equals to 0. As long as we have this 0 probability cannot be conditioned away, right? No matter the other evidence, means that for example, if this is 0, no matter how large other probabilities are, the probability here would be 0. And this apparently is not what we want. It's not what we want. So we apply this add one smoothing for naive Bayes. So the idea is that we reserve a small amount of probability for unseen probabilities. In that case, I mean, the probability would be very close to n, but not n. Very close to 0, but not 0, right? So it is small enough, but will not lead to a bad consequence, such that the total or the final probability would be 0. And so how do we do that? We add 1 at the fraction, right? So even this count is 0, we add 1, so make the probability will not be 0 anymore. Right. So we can the probability of observed events in this case have to be adjusted to make the total probability equals to 1. So in order to do that, for each denominator, we plus the size of the vocabulary. Then we can guarantee that the total probabilities, sum of the total probabilities would be. Now let's look at the whole procedure of multinomial naive Bayes. So how do we learn the classifier? So we firstly, from the training corpus, we extracted the vocabulary because we're going to use it to calculate the probability terms for PCJ and PWK given CJ. So we firstly compute the probability of CJ for different class labels. So for each class label in C, we firstly compute the number of documents that have with class label equals to CJ, right? And as we already know the total number of documents, we can compute probability of CJ easily. And in order to compute the probability of WK given CJ, we firstly we firstly construct the mega document where we concatenate the single document containing we create a single document that containing all documents J, which is all the documents with class label equals to CJ. And for each word WK in the vocabulary, we get the number of occurrence of WK in this text J in the mega document. And then we can compute the probability as this. Right. So alpha is equals to 1 if we use add 1 smooth. And this is also the default value of using this Laplace smoothing method. Right. So then we can compute the probability of Cj given D equals to a probability of Cj times the probability of Wk given Cj. So here, since log of x times y equals to log x plus log y, it is better to perform all computations by summing logs of probabilities rather than multiplying probabilities. This is a well-known trick to deal with, when you multiplying a list of numbers that are all smaller than 1, you would expect the result to be quite to getting smaller and smaller, approaching to 0, because all the numbers are smaller than 1, and the result precision would be hurt because because the float has only 24 bits of precision. So basically, when the number is too close to 0, you won't be able to distinguish them. All right, now let's look at an example of a naive Bayes classifier. So let's look at how we actually use this to help us to make the decision. So basically, the formula is here. So we firstly compute. Okay, so these are the training data, and this sentence is the testing data. All right. So for the class labels, C corresponds to China, O corresponds to OZ, which is Australia, and we firstly compute probability of CJ. So we only have 2 classes. So the first class, because in training data there are 3 documents has the class label C. And the total number of documents is 4, so it's 3 over 4. And for the same reason, it's we can have this 1 over 4 here. Then we compute the probability of WK given CJ. Note that in the testing in the test data, we only have Chinese, Australia, and Sydney. So we have these 3 distinct words. That's why for other words, for example, Beijing and Nanjing and Macau, here we don't need to compute their corresponding probability given CJ, because they are not involved in the computation of these 2. So it's C given document 5 and O given document 5, right? So for example, in order to compute the probability of Chinese given C, we first look at the documents that is classed that has label of C, which is document 1, 2, and 3. Here the word Chinese actually appears 5 times. Okay, and the total number of words in these 3 documents is 8. So that's why we use 5 and we put 5 and 8 here. But because of this add 1, add 1 smoothing, so we add 1 at the fraction, and we add 6 at the denominator. Right. So this 6 is the size of the vocabulary. So for the vocabulary, we have Chinese, Beijing, Nanjing, Macau. That's 4. Australia and Sydney. So in total 6 distinct words. So the size of the vocabulary would be 6. And alpha equals to 1, by the way. Right, so that's how we get probability of Chinese given C. And the probability of Australia, sorry, I missed an I here. So of Australia given C would be so for the label class, the class label of C, the documents have no Australia, so it would be 0 here. The denominator would always be the same. My machine was crashed before, so I've lost all the annotations. So basically, here would be a 0, and here would be 8 plus 6 would be the same for all, say for all probability of WK given class C. All right, so we apply this add 1 smooth. We've got 1 over 14 as the probability of Australia given C. And similarly, we can have Sydney given C is the same. And for O, because O we have Australia, Sydney, and Chinese, these 3 terms or words. So you can imagine that the number would be all the same. Here would be 3 plus 6. So for Chinese given O, because Chinese only occurs once in O, and the total number of words in the class label of O is 3. So this is the original one. Using add 1 plus, we plus 1 at the fraction plus 6 at the denominator, we would have this 2 over 9 as the probability of Chinese given O, and also for the same also the same for Australia given O and Sydney given O. Then we can compute the probability of C given D5 and O given D5. Here we're not actually compute the probability because if you still remember, the denominator has been dropped. The denominator is probability of D5 in this case. This has been dropped, so we can only get the number that the probability is to the proportional to. All right. So here we use multiplications, but you can also use you apply a log first, and then you use add. Addition would be the pretty much the same conclusion. All right. So basically, for the probability of C given D5, it is proportional to probability of C. So this is probability of C. This is the probability of Chinese given C, because Chinese appears 3 times in document 5. So we actually have 3 here. Have 3 Chinese given C multiplied together. And this 2 corresponds to Australia given C and Sydney given C. So finally, we computed the number would be roughly about 3 times 10 to the power of minus 4. Right. And similarly, we can compute the probability of O given D5, where you will get a smaller number. The smaller number. The actual probability is proportional to this number. So because then we know that the probability of C given D5 is larger than the probability of O given D5, then the conclusion would be D5 should be labeled as C. Right, so this is the prediction when you use a naive Bayes classifier. Okay, you will get this prediction. So to summarize naive Bayes, it is very fast and low storage requirements compared to other complex classification models, especially the neural network models. It is robust to irrelevant features because irrelevant features or irrelevant words canceled each other without affecting the results. So basically, as you can see, we even don't compute it. Right. It is very good in domains with many equally important features, because the hidden assumption, as you may notice in naive Bayes, is that each and every word plays the equally important role. Right. And it is optimal if the independence of some assumption hold. All right. So if assumed independence is correct, then it is the Bayes optimal classifier from problem. So apparently this is due to the Bayes, the Bayes rules. All right. And naive Bayes is a good dependable baseline for text classification. All right. So that is that's pretty much all for today. In Wednesday's lecture, we will briefly introduce other 2 classifiers because they will be used in the project, and we will then show how to use PySpark's machine learning library to build a pipeline to train the classifiers and to do the prediction. All right. And we will then introduce a little bit about the stacking method, that is to make use of different classifiers to achieve a better quality of prediction. And the project 2 will be using PySpark to implement the stacking method. Right. So that's all for today. Thank you for watching and see you on Wednesday.